In this video we're going to be looking at Chapter 19, the first lecture in Chapter 19, the very last learning objectives 4 and 5, looking at microstates and predicting the sign of S, as well as calculating delta S for chemical and physical processes. Okay, so let's first look at our 4 laws of thermodynamics. Our 0th law is our very first one that we look at, oddly enough, and it's that two objects in contact with each other at different temperatures will become the same temperature as they equilibrate, called thermal equilibrium. So two objects in contact with one another at different temperatures will equilibrate to the same temperature. We call this thermal equilibrium. Okay, our first law, which we looked at already, we looked at first and second already, but our first law is energy is always conserved. So it is neither created nor destroyed. Our second law, our delta S for our universe, is greater than 0 for a spontaneous process. And our last law, which we have not looked at all, is entropy of a perfect crystal is 0 at 0 Kelvin. So a perfect crystal, no flaws whatsoever. And at 0 Kelvin is 0. So basically everything has entropy. Okay, so we're going to look at our entropy of our surroundings. So we've looked at how to solve for our system a little bit, but now let's look at our surroundings themselves. So the surroundings are not necessarily going to be the negative of our systems, right? So they're not the same thing, a different sign, right? So we don't have to have conservation of entropy. So our surroundings themselves, surroundings, their entropy will be proportional to our delta H of our system. Right, so we're going to be looking at the delta H of our system to determine this. So our delta H of our surroundings, while also being proportional to the system, it's also going to be proportional to the temperature, right? 1 over temperature specifically. So our delta S of our surroundings will be equal to our negative delta H of system, divided by temperature. Okay, so what happens if we have an exothermic process? We're going to release heat. That heat is going to go into the surroundings. So if we're releasing heat, that's a negative value, but for entropy, we want that to be a positive value, so that is why we take the negative of that delta H. So when we release that energy into our surroundings is going to absorb it and become more disordered. And then it'll be inversely proportional to the temperature, right? If we have more disorder, but it's at a low temperature, or that a lower temperature disorder increase will be a greater amount of disorder. Okay. If we have our delta S of our universe, we're talking about our systems plus our surroundings. Anytime we have a delta S of our universe, That'd be greater than 0 for a reaction that is spontaneous. So one that is irreversible. If we have a delta S of our universe that is less than 0, we have a non-spontaneous reaction. And then if we have a delta S of our universe that is equal to 0, we have a reaction at equilibrium. And that is our reversible process. Or what we take our reversible process to be. Though it is not truly a reversible process, again, as I said earlier, because it's a state function, we can treat it like a reversible process, which makes calculating our delta S for equilibrium processes much easier. Okay, so let's predict whether we will have spontaneous processes, or what temperatures we'd have spontaneous processes for the following. So we have 2N2 plus O2 going to 2NO2. Everything's gases, right? So we have a gas plus gas plus gas. Our delta H here is a positive 113 kilojoules. So we have 3 gas moles. I guess I should probably write it down here. So we have 3 moles of gas going to 2 moles of gas. This is going to have a delta S that is going to be negative. Right? So this is going to be non-spontaneous, or it's going to be non-favored in that way. And then we also have a delta H, which is positive. So overall, we have a non-spontaneous process at all temperatures. Because our surroundings are also not increasing in heat, so they're not increasing in disorder. So our delta S of our universe is less than 0. Right? So if we have a positive delta H, we can't increase the disorder of our surroundings. If we have less disorder in our reaction, then our system will have less disorder, and we'll have a negative delta S. So overall, this gives us a negative delta S of the universe, which is 0. Okay, next one. We have 4 moles of gas plus 5 moles of gas going to 4 moles of gas plus 6 moles of gas. However, this has a negative delta H. So we would say that our delta S of our system, this one's the system, is going to be less than 0 because we're going from 9, oh wait, wrong side. It's positive because we're going from 9 to 10, so we're increasing our gas molecules. So we have a positive delta S of system. And then we also have a delta H, which is negative, which means our delta S of our surroundings is also going to be positive, right? Because now we're increasing the energy of those surrounding molecules, so they are moving more. As such, our delta S of our universe will be greater than 0. Okay, now we have 2 molecules of CO plus 1 molecule of O2 goes to 2 molecules of CO2, negative delta H. So here we have a delta S that is going to be negative because we are going to fewer molecules of gas. And then, in this first system too, and then our delta H is negative. So our surroundings is going to be positive, right? So it really just depends on temperature at this point. So we want our surroundings to be larger, so we want a lower temperature. So at a lower temperature, we're going to have a greater chance of being spontaneous. Okay, we looked at this kind of with delta G as well, same idea. Okay. So let's look at what happens to a gas in terms of entropy when it expands. So we've got the expansion of a gas into a vacuum. So this area right here is a vacuum. We're going to look what happens. So the expansion of gas into a vacuum. So this is always considered spontaneous. And we're going to look at why right now. What happens is there's always an increase in entropy. So we should be able to see if we're looking at one versus all the rest of them, or the first one versus all the rest of them, that there is more disorder. Just by the randomness of this. But we can look at it in terms of what we call possible microstates. So when we have just a few gas molecules hanging out in one bubble, and then we open it up to that additional bubble, we increase the amount of possible arrangements. So a microstate talks about a possible arrangement. And since we've increased the volume at which they can occupy, we have increased our possible microstates. So we can look at this with the following equation. S is equal to K, little k, ln big W, where S is our entropy, K is Boltzmann constant, which is 1.38 times 10 to the negative 23rd joules per Kelvin. And then W is the possible microstates. Okay. We can take this equation and manipulate it, and we can actually look at how our gaseous system changes as our volume changes. So we can solve for delta S for expanding gases, and an easier form than determining all of our possible microstates. Instead, let's look at the following equation, which is a little easier to solve for. So if we have an expanding gas, we can use the following equation, which is a manipulation of the equation we just saw, where we can actually determine what the expansion of the gas is. So we have to have an ideal gas, by the way. And that's because we have the gas constant, which is R. And here it is specifically 8.314 joules per mole Kelvin. And then N is going to be our number of gas molecules, or moles of gas. And then V2 and V1 are going to be volumes in liters. Okay. Liters or milliliters, really. It really doesn't matter. They're going to cancel out. So, because they're a ratio of each other, they will cancel out. So it really doesn't matter what unit you use. Okay, so let's try that using that equation. We've got a chamber containing 0.2 moles of an ideal gas at 27 degrees Celsius. It increases isothermally from 10 liters to 18.5 liters, and it has to be isothermal. So we want to know, in that case, what is our entropy. So we're going to take our delta S of our system equal to nR ln V2 over V1. Anytime we talk about expansion of gas, we're talking about this equation right here. So our number of moles is 0.200. Our gas constant, 8.314 joules over mole times by Kelvin. And then our volume, ln 18.5 liters divided by 10.0 liters. If I add this out, we get a delta S of system equal to 8.68 joules per Kelvin. Okay. And that is everything for this lecture of Chapter 19.